Hello, everybody. Thank you for joining us for the automated viscosity measurement webinar, Unlocking Polymer Characterizations. We appreciate your time. My name is Brian Palucci. I'm the product manager for the automated kinematic viscosity at Canon Instrument Company. I'm going to moderate the presentation. We'll make a link available should you want to review certain sections of this presentation at a later time. The presentation will take approximately 45 minutes. Then we'll have about 10 to 15 minutes at the end for questions. We're going to mute your microphone to prevent any distractions, but if you have any questions, please type them in the Q&A section. You will see the Q&A button at the top of your screen. At the end, we'll relay the questions to David and get them answered. If we don't get to all the questions, we'll get back to you and answer your questions individually. Dr. David Trowbridge earned his Master of Science and PhD from the Department of Polymer Science at the University of Akron. His research focused on the characterization of polymers by dilute solution viscosity, laser light scattering, size exclusion chromatography, field flow fractionation, and rheology. David collaborated with corporate sponsors of the Institute of Polymer Science through projects at the Institute's Applied Research Group dealing with the physical testing, failure analysis, processing, and molecular characterization. Prior to joining Canon, David continued his research at the Corporate Research Center and Chemical Division of the Goodyear Tire and Rubber Company, with a focus on the characterization of new and production polymers. Since joining Canon, David has provided technical guidance for the development of laboratory instruments and their applications. He also contributes to the design and production of standard reference materials and provides support for the company's quality system. I'll turn it over to you, David. Thank you.
Thank you, Brian. I'll be talking about, today I'll be talking about Canon's line of automated viscometers. I should say fully automated viscometers, because all the aspects of the polymer solution viscosity measurement are supported by the features of the mini PV. So the subject for today's talk is the viscosity measurement of polymer solutions, and I've divided this into 4 topics. At the start, I'll talk about the beginning and development of polymer science, because there's an important role of viscosity measurement at the very beginning. Then I'll talk about the motion of polymer molecules in a flow stream, because that is what's occurring in the capillary of the viscometer. Then I'll talk about polymer characterization that is based on viscosity data. Then I'll describe advancements in the polymer industry due to the automation of viscosity measurements. Now, I'd like to put into our minds the notion that viscosity probes the properties of polymers in solution. So that's going to allow us to realize that there's information about the polymer structure and size that's contained in viscosity measurement data. So in viscosity measurements, this is the concept. We have a shear field developed by the flowing fluid, the solvent, is surrounding the polymer molecule, and the vectors of the flow field, the shear field, are sort of poking at the polymer molecule, and the polymer molecule, being large, is sluggish, and its response is manifested as an increase in the viscosity. So it's reasonable that we can visualize that the enhanced viscosity is linked to the characteristics of the polymers that are dissolved. So going back to the beginning of the polymer science that I mentioned back in the 1920s, there was a class of materials that had unique properties, and it was the interest of a lot of scientists, but there wasn't a clear agreement about what the structure of those materials was. The prevailing idea is there was a colloidal structure, that there was small molecules that were aggregated together into a colloidal system. But Henry Staudinger took exception to that, and he made a proposal that the composition was actually that of large molecules that were formed by the repeated units that are bonded together by covalent bondings, like the bonds in small molecules, but done in succession until a large sequence is formed that he called a macromolecule. That was his term. And after macromolecule concept became accepted, the term also was used, called polymers, based on poly meaning many and mer meaning parts. So the concept of parts put together in large numbers is the idea behind polymers. Also, the idea that Hermann Staudinger was proposing with this concept of macromolecules. So in the image here, you can see the concepts contrasted with one another. We have the colloidal system idea put forward by most of the scientists, and then we have Staudinger's large coiled molecule that he was describing as a macromolecule. This was not easily resolved, and Hermann Staudinger's ideas were not immediately accepted, and he persisted with needing to champion his idea against the colloidal paradigm. And he got pushback from a lot of scientists. One prominent scientist, Henrik Weyland, said this to him: "Dear colleague, drop the idea of large molecules. Organic molecules with a molecular weight higher than 5,000 do not exist. Purify your products, such as rubber, then they will be crystalline and prove to be low molecular weight compounds." Well, Staudinger did not take that approach, but he did want to do experiments to support his idea of large molecules, macromolecules. So his notion was that he would chemically modify these materials, and the idea was that the modification would cause a dissociation of the aggregates and destabilize the colloidal state, and the material would revert back to a low viscosity if it was in fact a colloidal system. He was expecting to see that the viscosity would not go down because he's thinking that the molecules were covalently bonded together in large sequences and forming a large molecule, and that is in fact what he found. He made measurements using capillary viscometers. I'll show an image of it here in a minute, but the point, the underlying point of his first early experiments was that he got a persistent molecular weight based on consistently high solution viscosities, even after chemical modification. So this viscometer is the kind that he would have used. It's made out of glass, and it has several dimensions that are important that I'll describe in a later slide. But the takeaway idea that he presented is that solution viscosity was directly related to molecular weight. In fact, he carried this notion to a further level where he actually made a statement saying that the solution viscosity was quantitatively correlated to the molecular weight. And the viscosity he referred to, he described with the symbols eta in a square, or in these square brackets. This was the symbol for what was called Staudinger's index, which was the subject of much research for a long time following, several decades. The name eventually changed to intrinsic viscosity because other researchers, such as Mark Huey, Kuhn, Sakurada, and still others, this is names associated with the equation, they came up with this more general form because they realized that the molecular weight had an exponent on it, an A. In Staudinger's early analysis, A had a value of 1, but most nowadays, after the contributions of all these other researching efforts, the value of A for typical flexible polymers is a value of about 0.5 to 0.8. And so that general expression can be rearranged, and we can input a value for the measured intrinsic viscosity here and values for K and A and calculate a molecular weight. So this is a big advancement for polymer science and for solution viscosity. So Hermann Staudinger started to become satisfied with the wider acceptance of his macromolecular idea. You can see how satisfied in just holding a model of one. This enthusiasm was not shared by Weyman because, well, he kind of fell on the short side of the argument. Here's the manual viscometer I was mentioning, and I have now depicted the parts of it. There's a timing bulb. There's lines above and below it that you use to mark the meniscus as it's flowing through the capillary that's down below. So the capillary has a length and a diameter, and then there's a pressure head developed by the distance in the middle of the timing bulb to the bottom of the capillary. This is the driving head, the force due to gravity for transferring the fluid from the timing ball reservoir through the capillary. So this simple design gives exceptional precision. This was the favoring aspect of the instrument, and it had a stable force. The gravity was very reproducible, of course. At fixed dimensions, this was rigid glass, so there wasn't fluctuations in these important dimensions that are mentioned here. Also, the timing was simple. You just watch the meniscus drain through past the lines on the glass. And you have ability to control the temperature very well because of the shape of the viscometer, a U-shape, you can immerse it into a bath and control the temperature to a fraction of a degree. Also, there was outstanding accuracy because the flow in the capillary, as I said, was just simple laminar flow that followed basic laws of fluid flow, and also measurements were traceable to viscosity reference standards. So for all of these advantages, there still were cons. It's very labor intensive, and people using the manual viscometer had to manipulate the viscometer. That is, they had to be careful to handle the glass. They had to position it vertically. Vertical orientation was important to reproduce in the bath. You had to have exposure to the chemicals that are used when you're filling and washing the viscometer. You have to wait for equilibration time after you put it in the bath. It takes time for that material, the sample, to heat to the bath temperature, and then you have to be present to observe the flow and record the flow, and you have to then pull it out, rinse it off, dry it, put the sample in for the next measurement, and put it back in the bath and wait for the equilibration. So very time-consuming and effort-intensive procedure. Fortunately, the automation of the mini PV addresses all of these challenges, these cons, and I'll go over in 2 more slides where those automations come from and how they do this. Automation started with adding timing sensors and an efficient flow path to the manual viscometer. So again, the manual viscometer, which got wide use, also had a lot of methods written for it. In the methods, prescribed values for this volume, diameter, length, and height. So these are specified in methods, and we wanted to maintain these dimensions so we could have compatibility and compliance with the standard methods that have been established. So our new automated viscometer has the same dimensions of these important 4 that are specified in the methods as the manual viscometer had. So we've maintained consistency and validity in running the standard methods that are used widely. And let me just zoom in on this sensor here so you can see what this is. It's optical pickups that are positioned where the lines were. The lines above and below the timing ball that were used in the manual viscometer are now been replaced by these optical sensors that automate the timing. Now, we come to the next step where we put the viscometer, the automated viscometer itself, into an instrument. So that ends up with a complete turnkey system with computer control and data logging. This becomes a fully automated viscometer. But we start with the manual viscometer, as I said, because it has the great precision, and we want to retain these features. So as I said, we built an automated version of that viscometer, and in the process, we addressed 2 of the disadvantages. Observing and recording the time now is automated because of the sensors, and rinsing and drying the viscometer now is automated because we have a flow-through design. And then this tube, this viscometer tube, is put inside a bath built into the instrument. So the automated mini PV instrument has the bath constructed into it, and it also has the auto sampler with vials that holds 10 different samples. So we have 10 positions. This rack of samples will raise up and introduce vials one at a time into the tube tip, and the sample is drawn up into the tube by vacuum. And so the only material that is wetted is the glass in this section of the tube by the sample. Then when we want to wash it, as I said, solvent and drying air is introduced from the top to displace the sample and dry the tube. So all these features together give us the fully automated viscometer that has these features. It has tight temperature control, 0.01, 0.02 degrees C, plus or minus. Then we also have a wide chemical compatibility because this instrument is constructed of Teflon. We also have an integrated compressor as part of the instrument. We also have part of the instrument an integrated vacuum pump. These are the tools for controlling the solvent during the washing and the drying process. All these features together now have added to the advantages by making a rapid analysis and a continuous operation. The operator does not need to be present during the process of pulling the sample and making the measurements and washing the tube. Also, it's safe. It's isolation from the operator. It doesn't have the hands-on involvement that the manual viscometer requires. Also, we've had an extended range of operation, which I'll talk about in a few later slides. And we've also addressed the disadvantages of the remaining disadvantages of the manual. You don't have to handle the tube. It's built in and positioned in the bath, and it does not get replaced. Then we have also the fact that the temperature equilibration occurs more quickly. This is because the sample is loaded through the capillary. The surface area here for transferring the temperature into the sample is much greater than the surface area that's experienced when you're trying to heat up the sample in this large reservoir of the manual viscometer. So we pick up an advantage in the equilibration time as well. So all of the negatives that were mentioned, the cons, have been fully addressed in the automated viscometer. Now I'll talk about the flow, what's going on in the capillary. It's a laminar flow. This is represented by these rectangular vector for the fluid. It develops a parabolic shape during the drainage. In the vertical orientation, we don't need to have a pump. We're going to just use gravity as the force. And I'm going to introduce a particle into this flow stream because it's going to represent our molecule. And we'll look at it more closely in the vicinity of this particle to see what's going on a smaller scale. But what we see right away is that the particle is experiencing a velocity gradient, and that'll be more apparent when we zoom in. But before I do zoom in, I'm going to move the coordinate system to the middle of the particle. So we're going to be looking at the flow field from the perspective of the particle center. So there's the particle and the flow field. We have a new orientation of the XY axis. Now it's in the center of the particle, and we see that the vectors on the right are going down, the flow vectors on the left are going up, and that puts a torque on the particle and causes a rotation. And that's significant. And now we're going to examine this in even a closer detail by replacing the particle by a flexible polymer molecule depicted by this coil. So we still have the same coordinate system in the center of the molecule, and the flow streams are still in the negative direction on the right and positive on the left. And so we still have a rotation like we saw for the particle shown by these arrows, but we have now also a compression and a tension being caused. And because the molecule is flexible, it can have some amount of compliance to these forces, and you get deformations occurring in this molecule. And it was based on these realizations of the dynamics here that allowed the early theorists to come up with a dilute solution viscosity understanding that's based on the idea that these motions are available to influence the molecule, and the deformations are possible, but only if there's not influences from neighboring polymer molecules. So we want to make sure all the influence and all the response and due entirely to the flow field, the unperturbed flow field surrounding it of the solvent. So what this means to the experimentalist is he's going to isolate the polymer chains, separate them by surrounding them with solvent molecules. That means he's going to put it into solution, and in particular a dilute solution, so that the polymer molecules don't interact with one another or even influence one another. And because of that, concentration is an important aspect in this viscosity analysis, and it'll show up quite a bit in the following slides. And because of this, we made a instrument that's a companion to the mini PV, the Solution Preparation System, the SPS, which is simply a solvent dispenser and a balance, analytical balance. And these are controlled by a software package that we have written, and allows the user to specify a target concentration and then put a polymer sample in a vial and place it in the balance. And then the software reads the balance's mass and determines what volume to dispense from the syringe pump to add to the polymer to get the target concentration that's going to be required. So after that preparation is done, the polymer is dissolved for a period of time, and then it was available for analysis in the mini PV. So we get a quick and accurate concentration determination using the SPS. Now I'll talk more about the concentration by using this line to represent the continuum from basically no polymer to pure polymer, no solvent. So on the left, we have just the solvent, and we start to add polymer. So the concentration is increasing, and we get to a concentration that is a critical concentration because it marks the transition to the case where the polymer molecules are close enough together that they start to influence one another and eventually actually contact one another. So this is called the critical concentration, or sometimes the overlap concentration, because that's what's happening to the polymer molecules. If they get the concentration high enough, they start to interact with one another. But in the dilute region, there is no chain interactions. And then we begin to see interactions, and at another transition, another critical concentration, we start to see a persistence in the contacts between the polymer molecules that allow them to entangle, and we get even a different behavior in the concentrated regime here. So that is the situation in terms of concentration by itself, but we really want to consider also the influence of molecular weight, because molecular size is also impacting the space occupied by the polymer molecules. A larger molecular weight is a larger size. And so I put in this plot a combination of the concentration continuum in the x-axis and the molecular size in the y-axis. And I'll put a dashed line here horizontally to show M sub C, a critical molecular weight. Below this molecular weight, the polymer is not large enough to form significant entanglements. You can, above this line, if the molecular weight rises to this region, you can begin to form persistent chain entanglements. But below C star, as I mentioned on the previous slide, the molecules are isolated. And so they're not able to have the opportunity to make enough contacts to form entanglements. So down in the dilute region is where we don't have entanglements, even at the high molecular weights, where that could happen if the concentration was higher. Now, the interesting thing about this plot is that this line is at a slope. What that's saying is that at high molecular weights, C star, the onset to semi-dilute, is at a lower concentration because the molecules are bigger. They just cannot fit into the same space at a higher concentration. So the contacts happen at a higher molecular weight at a lower concentration. So that's an important aspect to remember as you're preparing solutions, that at high molecular weight samples, you have to maintain a lower concentration to maintain the dilute solution state. So in the dilute solution, if we maintain no contacts, we have the free mobility of the molecule to deform as required by the dilute solution viscosity theories that we'll be referencing later. At the other extreme, where there is no solvent, we would like to think about this state, but it really is not the state we're in. There's no solvent. The molecule is not swollen by the solvent action of the solvent working to expand the polymer. And more significantly even is that there's other polymer molecules in the very same vicinity forming entanglements. And I went to the effort to show these images, these pictures on the graph, because there's some measurements of some practitioners measure the melt flow, the viscosity of the melt flow, and try to relate it to the intrinsic viscosity. But you can see this, the state is very different. This is the state that's necessary and required to get intrinsic viscosity from the DSV measurements. The solution viscosity theories require this, and it's not even remotely the case for the melt flow state. So you have to be cautious if you hear or see numbers provided for intrinsic viscosity based on melt flow, because the state does not correspond to the free rotation and extension and compression that's required for the theories. So I want to quantify this concentration effect in how viscosity is influenced by it. I'm going to build an equation that shows that. So basically, the concept's going to be immediately obvious that the viscosity will grow as the concentration increased. And I'm just going to kind of build this in parts, and we'll see why that happens. So we'll begin with the solvent viscosity, and that's going to be the baseline with no concentration. We're going to have this viscosity, no polymer there. And then we're going to start to add polymer to get a solution viscosity. So it's a combination of the solvent viscosity and this term here that includes the solvent viscosity, but it's increased by a factor and by the concentration. And it's going to represent an increasing number of deformations that we're being sensitized, that we're sensing as we increase the concentration. And if we increase the concentration, we're going to be dealing now with interactions between the polymers. They're starting to influence one another at higher concentrations, and another term is required, and this term carries even more weight on the concentration because it's squared. And another term, this time cubed, is going to start to take into account actual physical contacts and overlaps with the polymer molecules. And this addition scheme builds into a series. It's going to eventually even take into account entanglements. So you can see from this little word story that the solution viscosity is going to begin first based on the solvent, and then all these additions are being added to it, and they are trying to take into account the compounding effect of the increased crowding that's happening to the polymer molecules as the concentration is going up, as it's increasing. Now I'm going to carry over that equation that we just saw into this slide here at the top, and I'm going to use this equation to develop what is the most fundamental of viscosity in polymer science, and that's the relative viscosity. And this is how we get it and what it means. It is, I'll just quickly state so we have that from the beginning, the relative viscosity is the solution viscosity divided by the solvent viscosity. And we're going to arrive at this by manipulating this equation that I developed on the last slide. So the first thing we can do is take the viscosity for the solvent out of each of these terms. You can see it appears in each one, but we take it out, we factor it out, and then adjust the remaining terms to be without it. And then we're able to take and divide both sides of the equation by that solvent viscosity, and here we have the form for the relative viscosity, written here with a typical notation of eta to with a subscript of r for relative. And the terms are just carried over from the parenthetical section of the previous equation. So this is the equation for relative viscosity, and this is a graph of what you would find. And you can see the dramatic increase as concentration increases. We have this curvature because of the higher order terms being dependent on powers of concentration. We see that kind of growth. If we work at lower concentrations, this term will become less significant. If the concentration is 0.1, cubing that is 0.001. So this term can get small when we go to low enough concentrations. And in fact, we do that, and we're left with an equation now that's just truncated at this term, and this becomes the working equation going forward, and the graph becomes much more manageable. You can see it shown here. So now I've taken that working equation that we truncated and carried it over into this graph, because I'm going to use that equation to show how additional viscosities are developed. I call these derived viscosities because they're based on the relative viscosity, but they start to incorporate considerations of the concentration in a different way, and they are given names that we want to remember because they're used in standard methods and different correlations with physical properties and flow properties. So the truncated working equation is here for low concentrations, and we can do some manipulations. We can subtract 1 from each side. So the numerator shows that 1 being subtracted from the relative viscosity here. And then we can divide both sides by concentration. So that puts the concentration on the left underneath the relative viscosity minus 1. And this is an important expression because it represents one of the derived viscosities, the reduced viscosity. And on the right side, the concentration from the first term goes away because of the division that we operated. Also, the concentration goes from squared to just a single power in the second term. Then Huggins looked at this, an early worker, and he realized that K1 is actually the intrinsic viscosity that Steininger had been using, and K2 is equal to a new constant times the square of the intrinsic viscosity. So Huggins made the substitutions of these into his version of the working equation, and this became referred to as Huggins equation. And you can look at this equation and realize that as the concentration goes down, as it even goes to 0, the second term will go to 0 because the concentration will drive the significance of all of this to be negligible. And what you're left with then is simply the reduced viscosity is equal to the intrinsic viscosity. And this becomes the definition of intrinsic viscosity. In mathematical terms, we say that the intrinsic viscosity is the reduced viscosity and the limit as concentration goes to 0. So that's significant because it gives us a method for analyzing and determining the intrinsic viscosity using Huggins equation. Graphically, it looks like this. You'll make several measurements. Here's 4 measurements shown. We get at different concentrations, and we get different reduced viscosities. And then we extrapolate the trend line for these data points to the y-intercept, which is 0, concentration at 0, and the intercept there is going to be the intrinsic viscosity. So this is one of the aspects of analyzing for intrinsic viscosity. In practice, often we combine that with a Kramer equation, which operates the same way as the Huggins. You can extrapolate to 0 concentration and isolate the intrinsic viscosity in a separate term that can be equated to the log of the reduced viscosity over concentration. So you can combine both of these equations in a dual extrapolation on the same plot and get a common y-intercept that represents the intrinsic viscosity. So this is a very powerful analysis tool, and it's been published in an article in the Journal of Society of Rheology, where it was written that measurement of intrinsic viscosity based on the extrapolation to 0 concentration is one of the most precise measurements in polymer science. It is also the simplest and cheapest method. So let me just review real quick. Our family of viscosities first begin with the relative viscosity, the ratio of solution viscosity and solvent viscosity. There's also a similarly related specific viscosity, which is the difference between solution and solvent viscosity divided by the solvent viscosity. So mathematically, that works out to being the relative viscosity minus 1. So these two, relative viscosity and specific viscosity, are the two fundamental viscosities from the solution viscosity measurements. But then we have this series of our collection of derived viscosities based on concentration. So we introduce concentration and we get the reduced viscosity. You saw this already talking about the Huggins equation. In the Kramer equation, we saw the inherent viscosity, and the intrinsic viscosity definitions we saw from the Huggins equation and the Kramer equation. So I want to mention the utility of the polymer solution viscosity, why we use it. It really falls into 2 categories. One is because it's a corollary to performance parameters. Physical parameters and processing parameters correlate with intrinsic viscosity and the other derived viscosities. And so we use it to optimize the conditions for processing like spinning, casting, coating, extrusion. And we also use it to target ultimate properties in products like stress, flex, stiffness, and stability. And we use it for characterization. It correlates with polymer size and shape, and this can be expressed as molecular weight or hydrodynamic size, or even the extent of interaction with solvent. So this is the usefulness that we find in looking at the polymer solution viscosity. I'm going to take a moment to show the simple three-step route to intrinsic viscosity and molecular weight. And on the way through this process, these three steps, I'm going to show the contribution of the mini PV and the SPS, the solution preparation system. So here are the steps. First, we determine the flow times. This is the contribution of the mini PV. It gives us the flow times for the solvent and for the solution, and allows us to calculate the relative viscosity. And actually, it is actually simply reduced to the ratio of the flow times. You don't even really have to calculate the viscosities from the flow times. In many cases, just the flow times themselves give you a simple ratio that'll give you the relative viscosity. Then you can combine that relative viscosity with the concentration, which is the contribution from the SPS. Allows us to get derived viscosities and, most significantly, the intrinsic viscosity. And then we combine the measured intrinsic viscosity with selected K and A values and incorporate those into the Mark-Ewing equation and use the form that allows us to calculate molecular weight. So this is the procedure that we follow and the important role that the mini PV and the SPS contribute. Now here's some data on the next slide that shows an actual experiment using intrinsic viscosity measurements on the mini PV. And I have here 4 concentrations done in duplicate. And I've extrapolated the Huggins equation and the Kramer equation. They have a common y-intercept, which is the intrinsic viscosity with a value of 0.797 deciliters per gram. And that corresponds to a molecular weight of 20,400 Daltons. This is for polyphthalamide and phenyl TCE at 30 degrees C. And I can get that molecular weight. Why? Because I've used the Mark-Ewing equation in the form that it gives us an opportunity to calculate molecular weight. I have the measured intrinsic viscosity, and the K and A values I got from the Polymer Handbook, which you may be able to see here in my stack of books. The first 2 large blue ones are the Polymer Handbook, and they have a very, very extensive collection of K and A values for many polymer solvent systems. Now, I like to show this slide and ones like it because it shows how much data is here, and I wasn't present for any of this measurement. It all happened while I was off doing something else, and I came back and was able to determine the IV and the molecular weight because of the automation of the mini PV. This is the strength that I want to bring to light, that you have this capability to do this and even more. You can start to change. You can go to extended concentrations and change solvents and see how that impacts the system. But on the flip side, some methods try to shorten the analysis by using what's called single point approach. Some researchers take these early working equations and made some manipulations, some assumptions, some approximations, and came up with expressions for intrinsic viscosity that are based on just one measurement of relative viscosity at one particular concentration. So that's why these are called single point approaches, because they estimate intrinsic viscosity based on just one data point, not involving an extrapolation like the more rigorous approach. But before you use these, it may be required in a method to use these, but if you use them with your own notion of saving amount of time and effort by using just one measurement, one solution, you should try to do the more rigorous analysis using the Huggins-Kramer extrapolation and compare the results to each of these 4 calculations and see which one corresponds best, and that would be your selection going forward. Now I'm going to do a quick comparison on the next slide with GPC, because GPC is a very popular and widely used analysis for polymer characterization in the solution. And I'm going to compare DSV, dilute solution viscosity, with SEC. And I'm going to look at the criteria in this circle based on efficiency, accuracy, precision, and capability. And I'll make the comparison in these rectangles based on these points or subpoints in the respective category. So for efficiency, let's look at throughput. Throughput for a DSV, I'm going to just say, is in most cases half of what it is in SEC. SEC can run to 45 or 30 minutes, and this can go down to 10 minutes. So there's some flexibility there, but that's a good ballpark comparison. Cost, the SEC is going to be at least 2 times more expensive than the DSC, and 4 or 5 times more depending on the configuration, the amount of columns that you use, and that kind of thing plays into it. Regarding maintenance, well, the DSV is actually more simple to maintain and more simple to operate. There's just less moving parts, whereas SEC is rather complicated. And that allows us to maybe jump over to discussing the accuracy. The driving force for DSV is gravity. So that's very stable, as I mentioned earlier. Driving force for SEC is a pump. And a pump has issues with consistency and maintenance. You actually, if you do a good SEC work, you should have a marker in your flow to give a measurement of the actual pump rate that's occurring for the analysis. There's corrections that might be needed to get good accuracy. It's really not relevant for the SEC measurements that we were talking about here. For SEC, or for DSV, I'm sorry. For SEC, there's several steps to the procedure that introduce uncertainties, like drawing the baseline, a very fundamental part of it. There's a selection criteria that has to be decided on, and you will lose some of the peak if you select, but you may incorporate noise in the baseline if you select on another basis. So even that by itself is introducing uncertainties, and that could allow us to talk about the precision. Those uncertainties accumulate and allow a situation where we usually see SEC having less precision, fewer significant figures than we obtain in the dilute solution viscosity measurements. And then regarding capability, in the context of flexibility and range, DSV has opportunities to operate at different temperatures, concentrations, and viscosities, and solvent selection as well. These are not easily available in SEC. You can do different temperatures, but it can impact the condition of the columns, and concentration can be varied, but it also impacts the retention time of the chromatogram. So you have to be careful if you try and manipulate these, but in an SEC, it's very straightforward, and you use less solvent, and the solvent doesn't have to be degassed or even filtered. Those are usually required for chromatogram work, SEC work. So in the end, taking this all together, what you see is there's really not a good reason to select SEC over DSV unless you need to see features of the actual chromatogram. And that would be the one reason why you would want to use an SEC. Now, I should also use this slide because it describes the precision that's available, not only the accuracy, but the precision of the DSV measurement. This is data that was obtained from the National Institute of Standards and Technology on a special reference material they have. It was a polystyrene 706 they referred to it as, and they measured the intrinsic viscosity, and I took a K&A values out of the Polymer Handbook for polystyrene and calculated a molecular weight using the Mark-Ewing equation and these K&A values from the Polymer Handbook, and I got a value for molecular weight and an uncertainty. And then NIST, for the same material, the polystyrene 706, did additional characterization measurements using light scattering and ultracentrifuge, and the molecular weight they got had an uncertainty of 8% using these other techniques. So the point here is this uncertainty. The IV, the molecular weight from the measured IV was much less uncertain than it was for the other techniques that gave a molecular weight measurement. And so that indicates a strength for the IV measurement. In fact, that strength was realized by some industries, in particular the plastics industry, and it uses intrinsic viscosity rather than molecular weight to categorize their materials. Here's a table of how polyester, PET in particular, is graded or rated based on a narrow range of intrinsic viscosities that are measured for these materials. So the viscosity, the intrinsic viscosity, is going to decide what application these polyesters or these PETs are going to be applied to. Here's an example of PET that was used, or I'm sorry, yeah, PET, but it was a virgin PET, and then some recycled PET that was blended with it. And again, intrinsic viscosity was used as a criteria to evaluate how the processing impacted with the polymer materials. So here they measured the intrinsic viscosity of the pellets of a virgin PET. I got a value of 0.78. And be mindful of the uncertainties that they're reporting for this intrinsic viscosity, very tight. And then they ran the pellets through their bottle forming process and saw a reduction in the intrinsic viscosity, which is expected. And then they did the same measurements for each of 4 particular recycled materials, saw the drop in the intrinsic viscosity. But what they were interested in was to see how the results of the intrinsic viscosity would be when they combine recycled PET with virgin PET. They did this in a 3-to-1 ratio and then measured the intrinsic viscosity after forming a bottle with that composition. And they looked at the intrinsic viscosity to compare it to the 100% bottle composition of virgin PET. And they're looking for a significance over the other recycled materials. And it points to sample C as being the best in retaining the intrinsic viscosity at a high level. So the point here is that this very careful analysis done with a lot of scrutiny was done with intrinsic viscosity. In fact, they stated that they initially attempted this with GPC. They studied molecular weight of the bottles by GPC techniques, but they reported that the deviation found in the repeated measurements for the molecular weights was larger than the difference between the values for the different samples. So what it meant was they had to give up on the GPC approach and redo the study using intrinsic viscosity because it could differentiate at this level. I think I may be running low on time, so I'm going to probably have to scoot through these other examples. This is an interesting one. The point here is that, again, they're using intrinsic viscosity with very tight tolerances. Look at the tolerances on these measurements. And they're using them to show how their chain extender, which is protecting the polymer from degradation, is very effective in maintaining high intrinsic viscosities. And again, they use intrinsic viscosity as the basis for their study. And I'm going to just flip through the details of this. But the point is, all of their arguments for the benefits of their product is based on these intrinsic viscosity results. And they repeat the measurements for other formulations of their material. They increase the loading of their chain extender and get also, again, increased IV values that are the basis for promoting their product. I wanted to mention some innovations that we are applying to intrinsic viscosity determinations. There's this recycling of polyvinyl butyrol. You can go to different applications after recovering it from laminated glass. So it's that plastic film that's inside safety glass, and you can recover that and apply it to different applications, but that's going to be based on the intrinsic viscosity. So there's an important application for recycling this material. And it's also done in other cases. This is a company that has our instrument, and they have a nice scheme to fully recycle fabric, and they digest it and form fibers again and put it back into fabric and get a full life cycle that's maintained and monitored by the intrinsic viscosity measurements of this material. And similarly, there's a company that has another mini PV in place in Southern California. They're measuring microorganisms found in the ocean, and they're converting it to natural biomaterials that are polymeric, and they're making items like reusable drinking straws. So they are basing their polymerization analysis on the measurements of intrinsic viscosity. Here's results of trying to determine if we're heating a sample too much during dissolution. It's an important consideration, sometimes hard to determine. So we dissolved a sample, and then we heated it for a little bit longer and measured the IV a second time. And here's the comparison. There's a 1.3% drop in molecular weight based on our analysis of intrinsic viscosity, which doesn't seem like much, but graphically, when you look at the Huggins-Kramer extrapolations, you can visualize that there is, in fact, some indication that's fairly believable that even a short additional amount of heating is going to cause some degradation that you should be aware of. Now, there's also an opportunity I want to take here to show the high precision applied to the analysis of chip-to-chip variation. Now, a chip is simply a term for a pellet or a chunk of a plastic sample. And the idea is that these plastic samples are not different from one another. When you take them to analyze them, you're assuming that every chip you take from the lot is going to be the same as the next. But in fact, that sometimes isn't the case because the sampling technique isn't perfect, and there'll be possibility of variation between the chips. And sometimes you want to confirm that you have chips that are representative of the lot. And so this experiment was an effort to do that. They took chips as is, made a solution out of individual chips or several solutions, and ran the IVs. And this is the intrinsic viscosity results. We're looking at the spread here of the values. And then they took pellets and ground them up into a powdery mesh, or through a mesh into a powder, and measured the IVs, and you can see they're much tighter for these samples. So we've removed some heterogeneity that was present in the pellets themselves and formed a more homogeneous sampling by forming a sampling from a powder generated by a grinding through a mesh. And so just this simple comparison allows us to see the utility of IV precision to make a determination on this important detail. There's even an offset here that we think is probably due to longer time for dissolution, so the more heat exposure for the chips. So the chips actually go down in IV because of that longer thermal history during dissolution. So let me summarize the features of the mini PV. So you have a constant temperature bath, you have fluid sensors to automate the timing of the flow, and we have an integrated auto sampler. All of these give us the opportunity to describe this as a fully automated viscometer. Also, of course, we have the automation of the washing involving the vacuum and pressure controls, and for also the data processing using a computer. Our software package is called VisPro. Let me make a quick summary of the applications that I mentioned. And there is a place, a solid place in the workflow in the lab for the IV because of its precision, its great throughput, its reliability. It also augments the the SEC and the GPC analysis. It can actually be used to compare to GPC results as a check to see if your GPC results are being consistent with the more reliable IV determination of the DSV analysis. And you can also quantify polymer solvent interactions. I didn't talk about this very much, but the coefficients in those working equations tell you something about the interaction between the polymer and the solvent. It might give some indication of maybe chemical composition of various copolymers and how it might be varying between samples. And then also the precision allows you to differentiate between very similar samples. Also, the IV measurement using DSV technique and the mini PV in particular gives you an opportunity to maybe offload some of the SEC work. If you're looking at an average from your DSV measurements, you're going through a lot of steps to fractionate it and then reconstruct an average. It may be better to just measure the intrinsic viscosity directly and use it to control your release specs or the processes that you're already maybe looking at a molecular weight that's not quite as reliable or has as good resolution for these control steps. So in final summary, mini AV, the fully automated construction gives you direct measure of IV, a stable design for fast results, unattended and safe operation, and high quality data with exceptional precision. And I want to end with one endorsement that I particularly like. This was taken out of a polymer physics textbook, and they said, owing to the superb precision of viscosity measurements, the intrinsic viscosity can easily be measured to 3 significant figures, which makes it by far the most precise polymer characterization method. And that's the end of my presentation, but I was given a slide that I wanted to share because this is a new product line for us at Canon, and I wanted to introduce it to us here in the audience. That we are now looking at sharing the product line for Hitachi for instruments of thermomechanical analysis. So we have a DSC that we're offering to measure TG and melting temperature and heat capacity. And we have one that combines that with TGA measurements to look at degradation and composition. And then we have a thermomechanical analyzer, and we have a dynamic mechanical analyzer. So these are all available, and you can ask if you're interested, the host, to get more information about this product line that we're kind of excited about. So thank you very much, and I have my contact information and are able to answer questions now.
Thank you very much, David. That's a good way to end it. Looks like we have time for a few questions. If we don't get to all the questions, we will get back to you individually. So I see one question here. Does the auto sampler work well for dilute solutions and volatile solvents?
Yes, they are capped with an aluminum foil, and they have an additional septum that seals around the tube tip so that during the measurement, it's a contained system. The vial is contained and the tube tip is isolated from the atmospheric air. So we have a closed headspace above the vial.
Okay, thank you, Dave. There's another question here. Is it any dilution value per each type of polymer molecule so the end user knows how to be below the variable C star?
Oh, I think, can you say that question again? But it's a very important one, I believe. I want to answer that if it's what I think. Can you say that again?
Is it any dilution value per each type of polymer molecule so the end user knows how to be below C asterisk?
Yeah, that's what I thought. There's a rule of thumb that says that C star, the critical overlap concentration, is simply the inverse of the intrinsic viscosity. So if you already have an estimate for the intrinsic viscosity, then take the inverse of that, and that's the concentration you have to stay below. That would be true for different polymers and even for the same polymer at different molecular weights. You'll remember that one graph I showed that the C star followed a slanting line, and that's because at higher molecular weights, that critical concentration is going to have a lower value. That's actually written into some standard methods. They say if your molecular weight is suspected to be high, then we want you to prepare your solution at, say, 0.1% instead of 0.2%. Or if 0.5 is typical, they'll say prepare it at 0.2 if the molecular weight is greater than, say, 500,000. So this is specified in some methods, but if you don't have that guidance, you just can use an estimate of the intrinsic viscosity and look at the inverse.
Okay, thanks, David. So I think this concludes our webinar today. Please feel free to follow up if you have any further questions. We'll be happy to get back to you. Thank you.